魏廷、李荣兴、施和同、黄元雄不在，王淑婷，华德阳，赵明玲是你啊，黄兆伟，浩，那是浩吗？那是
写不太清楚。
哦 ，OK， 好，黄浩伟，好，赵廷伟 ，OK， 还有施和同跟黄元雄不在，施和同还是黄元雄？你是不是？好，暂时放在这里。Okay, now, we proved a couple of weeks ago a theorem about the equivariant cohomology of a free action, right? So what did we prove? What do you remember about the cohomology of a free action? A free action, that's when the stabilizer of every point is the identity. Okay. So do you remember what theorem we proved about the cohomology of a free action?
The cohomology of
The equivariant cohomology is always the cohomology of the homotopy quotient, right? And you know that the equivariant cohomology, right, is, it's U torsion, okay? It's an R of U module, but if the action is free, then the equivariant cohomology is U torsion. Okay, that's what we proved. And we want to generalize that to a locally free action. Okay? So what's the difference between a free action and a locally free action? Yeah, it's locally free if the stabilizer is discrete. Okay? So definition. The action of a topological group G on a topological space X, okay, is locally free if the stabilizer of every point is discrete. For all points in X. Okay? So that's what we want to look at today. Okay? So I'm going to first prove a proposition that if okay, now I'm going to assume that we are in the smooth category. So the group is a Lie group. If a Lie group G acts smoothly on a manifold M, then for all X in the Lie algebra, but not zero, the fundamental vector field X bar is nowhere vanishing. Oh, no, just a minute. I want to assume that the action is smooth and locally free. Okay? Locally free. Smoothly and locally freely. Okay? Yeah. So, when you rotate the sphere S2 about the z-axis, okay? Now, the action is not locally free because you've got these two fixed points. Okay? But if you remove the two fixed points, then the action is locally free. Because, in fact, it's free. And so you see that a vector x in the Lie algebra of the circle, right, it's going to generate this fundamental vector field on the sphere. And on the locally free part, you see the fundamental vector field is never zero. Okay? So the example is that S1 acts locally freely. In fact, it acts freely on S2 minus the North Pole and the South Pole that we call P and Q. And in the picture, you can see that that fundamental vector field is not zero. But if you include P and Q, then the action is no longer locally free. And then the fundamental vector field vanishes at those points. Okay? So this is a very easy proposition to prove. Okay? Because suppose the fundamental vector field vanishes at some point P, for some P in M. Then what's an integral curve of this fundamental vector field that starts at P? Pardon? Constant, right? Then the constant curve C of t is equal to P is an integral curve. Of the fundamental vector field, okay, through P. Okay, that means the initial point is P because if you take the constant curve and you differentiate it, you get 0, and that is x bar at P, and that is x bar at the curve C of t. So that says that C is an integral curve, okay, of the vector field x bar. Okay. But we know that in general, there's a formula for the integral curve, right? There's a formula for the integral curve. Is also an integral curve for x bar through P. Okay? And we proved that formula a few weeks ago. Okay? So do you remember the formula for the integral curve? Pardon?
Is this right or left action?
Well, this is a left action. In general, if I don't say anything, then it's a left action. It's what?
Exponential minus 3 act on.
Yeah. So the formula is you take e to the tx, that's an element of the group, minus tx because it's a left action, and then you apply it to p, okay? This curve is also an integral curve of the fundamental vector field, okay? And for any vector field, if you fix the initial point, then the integral curve is unique. So by the uniqueness of the integral curve, through a point, then you know that the two integral curves have to be equal, okay, for all t in R. Okay? Yeah. Now, how is that a contradiction? To the proposition. Here's the proposition. Yeah. So the hypothesis is that G acts locally freely. Okay? So how is that a contradiction? Yeah, because then this says that this is in the stabilizer of P, right? But this is not just a discrete set of points. This is a curve, okay? Then, so the stabilizer of P contains a curve, e to the minus tx. Okay? And so the action is not discrete. So the stabilizer is not discrete. And this contradicts the hypothesis that the action is locally free. Okay? Yeah. Yeah, that's my symbol for a contradiction. Okay? And right, so the contradiction proves that this can never be zero. The fundamental vector field cannot vanish if you choose a non-zero x to start with. Okay? Yeah, if x is zero, then you just get the identity. You get a single point. So you don't have a contradiction. But if x is not zero, you get a curve. So you get a contradiction. Okay? Okay. Okay, so now I want to prove that, let me see, I'm going to specialize more and more. Okay, so this proposition is for a Lie group, and now I'm going to assume that the Lie group is compact and abelian. Proposition. If a compact abelian group acts locally freely on a manifold M, then there exists a G invariant one form P on M, okay? And then I have to fix a non-zero element in the Lie algebra. Okay. Then there exists a G invariant one form on M's such that phi of x bar is 1, identically 1. Okay? See, we'll need this one form in order to construct an equivariant differential form for a circle action, okay? Because an equivariant differential form is simply a polynomial in U whose coefficients are invariant forms. Okay. So now what do the hypotheses tell us? Okay, so recall that now if you have the fundamental vector field, right, and you let's translate it by G. So we had a formula for this, right? Do you remember that formula? When you left translate a fundamental vector, it becomes another fundamental vector, okay? And it will be at GP. But what Lie algebra element do you get there? You get the adjoint of G inverse times X. Okay? So we have that formula. Let me see. Oh, I think you are. I think that's the formula for right action. Right? Yeah, for right action, you have a G inverse, and so for left action, actually, you have a G. Yeah. Okay. But in any case, if the group is abelian, then the adjoint representation is the identity, right? Because its conjugation is the identity. So the adjoint representation, so you just get X bar GP if G is abelian. Okay? Yeah. And so that says that, X bar is a left invariant vector field. Okay? So to prove the proposition, now I have to define a one form. So I define for all P in N, phi of P. Okay, phi is a one form, so it takes the tangent space to R. So I define phi of P by this formula. Okay, if I have a tangent vector ZP, sorry, and okay. Now this is one thing. That comes from the hypothesis that G is abelian, okay? But G, we also assume G to be compact, okay? So if you have a compact group acting on a manifold, now you know that every manifold can be given a Riemannian metric, okay? But if you have a compact group acting, what can you assume about that Riemannian metric? This was in problem set 1. In problem set 1, I ask you to prove that
Then you could make it invariant.
it's G invariant. You have a G invariant Riemannian metric if the group is compact, okay? Because you can integrate over the group. So this is 1. And then 2 is that a manifold with the action of a compact Lie group has a G invariant Riemannian metric. Compact Lie group action has an invariant metric. Has an invariant Riemannian metric. Okay? Okay, so I'm going to assume that I have an invariant Riemannian metric, and then I define a one form by this formula. Okay. XRP ZP. That's going to give me a real number, and then I divide by X bar P square. Okay. That's just to make sure that if I apply it to X bar P, I will get 1. Okay. Where this is a G invariant Riemannian metric. Okay? So I have to check two things. The first thing is that if I apply it to X bar P, I get 1. So check that phi P X bar P is X bar P over the length of X bar P square, and that's 1. Okay? So that part is good. And then I have to check that it's left invariant. Okay? So let G be in G. Then I look at the left translate of phi and apply it to ZP. Now, by definition, this is phi at GP applied to the push forward. Okay, so that's the definition of the pullback. And then by the definition of phi, this is X bar at PG at GP LG lower star ZP over X bar at GP X bar at GP. Okay? That's the definition of phi. But because G is abelian, X bar at GP is the push forward by LG of X bar at P. Okay? So this is because G is abelian. Okay? And now because the metric is G invariant, that means this is the same as x bar p, x bar, z, here it should be z, zp. Sorry, yeah, that's right. Yeah, zp on the top, okay? So, so that's equal to x bar p zp over x bar p x bar p. Okay? So because the metric is G invariant. Okay? And this is the definition of Vp as Zp. Okay? And so what this proves is that when you pull back by Lg, you still have the same one form. Okay? So, hence, phi is G invariant. Okay. So I have a G invariant one form that gives me the constant 1 if I apply it to the fundamental vector field. Okay? Yeah. Okay. And so now we can prove our theorem about the equivariant cohomology of a locally free action. Okay? And we are going to prove it by using the Cartan model. So the Cartan model for a circle action on M is, okay, so the Cartan model, that's a differential complex. So instead of using ordinary differential forms on M, you use equivariant differential forms, right? And so what are the equivariant differential forms for a circle action? It's yeah, the polynomials in U with coefficients in the invariant forms. Okay? So that's the Cartan model. And then you have the Cartan differential dx, where dx of alpha is equal to, so do you remember the formula for the Cartan differential? Yeah, d alpha minus u I x alpha. Okay? Now, there's one thing I want you to check as a homework problem, that if you define dx by this formula, then it's an anti-derivation. Okay? So dx on the Cartan model is an anti-derivation. Of degree minus 1. Okay. So that just means that it lowers the degree by 1. You see, here, degree plus 1, yeah. it increases the degree by 1 because d alpha, that increases the degree by 1. Okay? And then Ix alpha decreases the degree by 1, but u has degree 2. So this term here also increases the degree by 1. Okay? So it increases the degree by 1, and it's an anti-derivation. Okay? That means it behaves like the usual exterior derivative. Right? You see, d is an anti-derivation, Ix is an anti-derivation. So actually, dx is also an anti-derivation. Okay? And then we are going to localize. So if you have an anti-derivation of R of U algebras, then when you localize with respect to U, it's still an anti-derivation. Now the coefficients will be R of U, and then you localize with respect to U, so that means you are allowed to have U inverse in the... just a minute. No, let me see. I don't think it's that. I think it's just this. Okay. Yeah. This means you're allowed to have powers of U in the denominator. Now, is it the same as... yeah, if you have a polynomial in U inverse, that's right. Yeah, that's the same as R of U inverse. Right. Okay, yeah. So, I mean, that's very straightforward. And that will be in your homework. Yes, I will give you your homework, the final problem set on Friday. Okay. And you'll have 2 weeks to work on it, and that will be it. Okay. So we want to prove this theorem that if S1 acts locally freely on a manifold M, then the equivariant cohomology of M is U torsion. Okay? That means it's annihilated by some power of U. Every element is annihilated by some power of U. Okay? And now, what's an equivalent algebraic statement that some module is U torsion? Right? We proved that last week. So a module N is U torsion if and only if... Yeah. If it's finite dimensional, if it's a finite dimensional vector space, yeah, it will be U torsion, right? But the converse isn't true. So you can have an infinite dimensional vector space that's where every element is killed by some power of U, right? But yeah, we had a very simple criterion, right? Right, a module N is U torsion if and only if the localization with respect to U is 0. Okay? So it suffices to show that the localization with respect to u is 0. Okay. And now, by the equivariant Durand theorem, you can compute the equivariant cohomology from the Cartan complex. By the equivariant Durand theorem. So, the equivariant cohomology is the cohomology of the Cartan complex. Okay, where you fix some x in the Lie algebra of the circle. And x is not 0. So in the Lie. Okay. And so if you localize the cohomology, because localization commutes with cohomology, you can localize the differential complex first. Okay? So you can localize this first and compute the cohomology of the localized complex. Okay? So this is because localization commutes with cohomology. So the localization of the cohomology is the cohomology of the localization. Okay? So that means now you can use the Cartan complex to compute to compute this localized equivariant cohomology. And so that just means that you can invert u when you are doing your calculation. Okay? And now I already have, we have a G invariant one form. Here G is S1. We have a S1 invariant one form such that phi of x bar is 1. Okay? And so this invariant one form is in the Cartan complex. Right? And so we can compute dx of no, just a minute. Let me just make an observation. You see, we want to show that the cohomology of this complex is 0. Okay. Now, to show that the cohomology is 0, normally you find a cochain homotopy K, so that dk plus kd is the identity, right? Yeah. But here, when you localize, there's a simpler way. So it suffices to show that the cohomology of the localized Cartan complex is 0, it suffices to find an alpha, okay, in here such that dx u of alpha is 1. Okay. Why is that? Well, okay, now let me first simplify the notation because, yeah, it's not good to have two subscripts. So we will write dx for dx u, okay, and d for du. That is, when we localize, we use the same notation. Okay, yeah. Then you see, so dx of alpha. Dx of alpha over u to the m no, normally it should be this, right? dxu of alpha over u to the m. By definition, it's dx of alpha over u to the n. That's how we define the localized map. Okay, but so in my new notation, this dxu I'm just going to write as dx. Okay, so there's no confusion, all right, because so dx can be now applied to a fraction, and you get that. That's the definition. Okay, and now suppose you can find such an alpha so that dx alpha is 1. Okay, then, okay, if dx alpha is 1 and z is any dx cocycle, then z will be equal to dx alpha times z, right? Because dx alpha is 1. But this, you can write this in another way. Okay, this is dx of what? Alpha times z. Because alpha is an antiderivation, so when you expand, you have this term dx alpha times z plus alpha times dxz. But dxz is 0 because it's a dx cocycle. Okay? So this is because dxz is 0. Okay? So what this shows is that if you can find an element dx alpha such that dx alpha is 1, then any cocycle is a coboundary. Z is dx of something. Okay? Yeah. Okay. Therefore, this is all that we need to do. We need to find an alpha so that dx alpha is 1. Okay? Then the cohomology of the localized. Okay, so now let me try to find that alpha. So now I have invariant one form, so the phi of x bar is 1. Let's see what happens if I apply dx to this phi. Dx phi is d phi minus u ix phi. Okay. And ix phi, what's ix phi? 1, because that's just phi applied to x bar. So, so I could just get u there. Okay? Yeah, ix phi, no, we don't put a bar there. You see, ix phi is defined to be ix bar phi, that's phi of x bar, and that's 1. Okay? Okay. Now here is where it's good that you can invert u. Okay? Because now you can divide by u. So dx phi over u is d phi over u minus 1, and that is minus 1 minus d phi over u. Okay? And then, you see, the thing is, I can invert this because it starts with a 1. So I get minus 1 minus d phi over u minus 1 times dx phi over u is 1. Okay? And and what is the inverse of 1 minus d phi over u? In any algebra, 1 minus x, you invert 1 minus x. What do you get? Yeah. You see, yeah, it's just a geometric series, right? Okay? But here you have a 2 form. Okay? So a 2 form eventually, if you raise it to a very high power, it will become 0, right? Because the manifold is finite dimensional. So here what you have is minus 1 plus d phi over u plus d phi square over u square plus, let me see, I think, yeah, if you raise it to the n minus first power, it's going to stop because, just a minute, let's write down the rest. Okay, so because the next term is d phi to the n, and that has degree 2n, right? Because d phi has degree 2. And this is a form of degree 2n. Now 2n is greater than n, right? Yeah, if n is not 0, 2n is greater than n, because 2 is greater than 1. N is a dimension of n, and not 0. 2n is greater than n, so d phi to the n will be 0 on n. Okay? And therefore, this power series will terminate at this point, maybe even earlier. You know, this could be 0 too, but certainly it can go only this far, And okay, so now let's see. You see, I'm going to show that. I want to show that this is closed. Okay, so how are we doing for time? Okay, I think I need to stop here. So we'll continue after 10 minutes. Okay. So. To be continued. Yeah. Yeah, I'm almost there. I have 1 is equal to something. I just have to show that this something is dx of alpha. I just have to show that this is exact, okay? So that we will do in 10 minutes. Let's see, so let's take a break. 师和同, okay, and then 黄, is it the 袁? 黄元雄, 对不对? 好, okay, thank you. All right. Okay, so